Kay hat ja schon auf dem Platz des Bundeskanzlers Platz genommen. Und ich freue mich auf einen Vortrag, der sich mit der Geschichte der Nutzerschnittstellen, insbesondere der grafischen Nutzerschnittstellen, beschäftigt. Alan, please.
So whenever you get invited to a conference that has pioneers in its name, I think it's a celebration that we're just still alive. Of course, all of the rest of these guys are much older than I am. So I thought instead of just talking about some of our work during a brief period, it would be interesting to give you a sense of what user interface design was like in the 60s and 70s. I'll include some of the stuff that we did at Xerox PARC, but as Newton said, he got as far as he did by standing on the shoulders of giants, and we certainly did. And I think you make revolutionary process if you can stand on the shoulders of giants and try and jump in a different direction. And we certainly tried to do that as well. So the first thing I'd like to just show is that we're set up by nature to think normally, which means like McLuhan's fish here, who doesn't know that it's swimming in pink water. And he meant that we are the fish, and the context and our beliefs are this colored water that we can't see. And an interesting model of thinking, very simple model, was done by Arthur Koestler some years ago, and he took the pink water from the goldfish bowl and spread it out and made a plane and likened normal human thought to an ant crawling about on this plane, and pointed out that the ant can have the illusion of progress, and that the ant can choose directions, it can see goals, it can get around obstacles, but no matter what it does, everything it does is pink. It has no sense of other dimensions of thought, but in every action there's a little outlaw vertical thing, a blue action. So we might have a little hint of a blue idea, but we've all gone to school, we all have parents, we go to church, we grow up in a particular place, and so there's this kind of kersplat that comes down and beats us back into orthodox ways of thinking. But every once in a while, in an unguarded moment, taking a shower, waking up in the morning, out jogging, you suddenly get an outlaw idea, an idea that can't stand to be confined in the pink plane. Now, how many people in this room have had one of these epiphanies? So it seems like it comes from heaven, and back in the old days, people would start religions because these ideas seem to be so true. Now, it turns out that all ideas, whether they come this way or come regularly, almost all ideas are mediocre down to bad. So the main thing you want to do when you have an idea is take a nap. In Western society, we act way too much. We don't think nearly enough. But we also now have the methods of science for dealing with these inspirations, and they allow us a pretty strong way of testing out whether this idea that seems to come from heaven actually has any substance to it. And Koestler pointed out that we have one of three emotional reactions, or some combination. So if somebody is telling you a joke, which is one of the simplest forms of these, a joke is leading somebody down the pink plane and suddenly revealing it's about something very different, you start laughing. And if it's science, you have this aha reaction. And sometimes you start laughing because the thing that's funny about science is just because we had a new idea, the universe didn't change to accommodate it. The universe was like that all along, and these insights were just hiding from us. And if it's art, then we have this long, drawn-out sigh. And one of the purposes of art, particularly great art, is to remind us that there are these other contexts. And then the difficult thing about having a new idea is it takes almost as much creative effort on the part of everybody else to understand this new idea. This is why we had to set up schools a few hundred years ago, because these invented ideas were starting to appear, and they were very difficult to learn because they require a kind of a rotation in normal human common sense thinking. Now, in the early 60s, I worked my way through school as a systems programmer, but I wasn't that interested in computing. I was just using it as a job. I was in molecular biology and pure mathematics. Math I was interested in was the math of algebras, abstract algebras. And molecular biology was just starting to happen. Then in 1965, there was this great book here. And this book a lot of it was about this bacterium that we have millions of in our stomach called E. coli. And by doing some calculations, which are not in this book, I discovered that one of these little bacteria had about a megabyte of DNA. That was a lot of computer back in the 1965, and it had 3,000 types of large protein molecules, about 5 million in total. They were running very, very quickly, and they reproduced every 20 minutes. So there's this enormous amount of activity going on, all powered by the kinetic motion of heat. And I also knew that these bacteria were about 1/2000th the size of the cells in our body. So cells in our body are about 2,000 times larger. So this is about the relative scale of these things. And we have about 1 billion of our cells just in the first joint of our thumb. Give you an idea. And if a cell were the size of a grain of rice, then our thumb would be about the size of a living room in your house. That would have 1 billion of these cells. And each one of these cells has about 60 billion components that interact informationally. And Tom Watson here has, and we have about 100 trillion cells. So this is a kind of a different way of looking at life that appeared in the 50s and 60s, and it was just in my mind when I suddenly decided to go to graduate school in computing. And especially the computer pioneers will remember just how large machines were physically back then and how small they were logically. I think there was a fantastic, somebody, you'll remember, Tony, there was a fantastic Algol compiler by a guy by the name of Brian Goodman, that had something like 200 passes. It was on a machine that had, I think, only drum memory, and it had a very small amount of it, so it had to constantly move the tape back and forth, doing a little bit of the compilation each time. And the thought of programming was mostly in terms of algorithms and data structures, not in terms of systems back in the early 60s. But things are starting to happen. I was an ARPA graduate student, and one of the things that I found about shortly after I went to graduate school was Ivan Sutherland's Sketchpad. And Sketchpad was kind of the dawn of computer graphics. It was done in 1962. And so it had this notion of graphical objects. It actually had a clipping window. It had icons. And here's kind of what it looked like. So things were done with a light pen. You'll see his hand go up and dip into the ink there. He's manipulating buttons on the side. So he's going to draw a flange. He doesn't draw it very carefully because he can draw this thing and then he can point to the parts of the flange and then he can tell Sketchpad to make them all mutually perpendicular. Sketchpad is doing that right now, and it just figured out how to solve that problem. So you notice the clipping window. The actual canvas that he's writing on is about 1/3 of a mile square. There's plenty of room for drawings. Again, he's saying make these guys parallel, and they were already attached to the sides of the flange, so it figured out that problem. So in each one of these cases here, now the constraint is collinearity for making these little dashed lines. By the way, this is not a line drawing display. So every little dot is being plotted individually by this TX2 computer, which is about the size of this room. Now he tells those lines to be invisible. Now he's got a hole through the flange, zooms back out. Now he wants to make a rivet. Same idea. Notice he flicks that pen when he wants to break the line drawing. He chooses that as the center for the radius of this arc. And now he points to these lines and says, make all of these mutually perpendicular. And notice what it does. It pulls the lines together, centers the arc, and makes a nice little rivet. And he could also constrain the proportions of these guys if he wants. Here he's just showing you that they're in this under-constrained thing that he's made. There are a number of different solutions for making a symmetric thing. He wants something that looks more like a regular rivet here. And what's cool about this is that this is not just a rivet. This is what he called a master for the rivet, what we'd call a class today. So now he's going to make some instances of this rivet. He can move them around. He can make them, turn them. Make them any size. See, this program brought demands for better displays. Now he's going to prove to us that he can have multiple instances of this rivet. And then he remembers, oh, I don't like the cross guys, so I'm going to make those invisible here on the master drawing. And guess what happens to the instances? They all reflect that change automatically. Now he's just made a master of that construction that he made. So he's taken those two classes and composed them together. And now he can make instances of these flanges with a rivet in it. And again, each one of them has its own parameters. Okay, so that's Sketchpad. So in many ways, all of the stuff I've done, except maybe aiming it at kids in the last 35 years, has been kind of putting a footnote to these insights in Sketchpad. I wanted to ask Ivan Sutherland, how could you possibly have sort of invented computer graphics, done one of the first object-oriented software systems, and done an automatic problem-solving system all in 1 year by yourself? And he said, well, I didn't know it was hard. What's interesting about this, we would be very pleased, many of us, to have a graphics system. We'd like the display to look a little bit better, but we'd be very pleased to have a graphics system that was this flexible, that had this look and feel to it. So here's a the way you defined operators in Sketchpad was composing constraints. So here's a parallel, here's an equal constraint and a parallel constraint. And you could pick, this is a graphical object as well. You could pick this up and drop it into here, copy it, and then you just merged the constraints with the lines that you want to deal with, and the parallel and equal constraints would make this thing into a rectangle. Then the interior of Sketchpad, you can imagine what it was like to try and read this thesis back in 1966. Still just 3 years after it had been done, and eventually it dawned on me that here, this is an instance, what he called a generic block, and at some point it dawned on me that each instance opposite 1, 2, 3, 4, 5, the sixth word down here, had a subroutine in it that knew how to display the particular type of thing. So if it was a line, it knew how to display the line, and if it was a point, it knew how to display the point. And this is the first time I ever saw what we call polymorphism today here. And this idea, by the way, he didn't completely think of. It was actually also in a very, very early paper by Doug Ross, who was doing some design graphic stuff at MIT at the same time. And there was even kind of a class hierarchy in it, where he had a bunch of different kinds of things he called variables, things that held things. He had a whole set of things that were called constraints. So these are kind of super classes. Each one of these guys was a class, and then you could get instances of those things. So this is an extremely sophisticated gem of a system. Maybe my vote for the greatest single thing ever done in computer science by one person. It's almost astounding, even to go through and read the thesis today. And one of the wonderful things about it was that in his thesis, every other page, he apologizes that the system didn't do more. Because when he started this out, he just wanted to do the whole, everything you could do in computer graphics with this thesis. By the way, all of these pictures here were drawn in Sketchpad for his thesis and plotted out. One of the few graphics theses ever in which the computer graphics done by the graduate student was actually used to produce the images in the thesis. Well, next thing I encountered in my first 2 weeks of graduate school were a pile of tapes and listings from none other than Kristen and Ole Johan. They didn't know it, but we had a UNIVAC 1108 at Utah, and I was the latest graduate student, and the tradition there was the latest graduate student got the latest dirty task to do. And so there's a note on it that basically said, this is the algol for the UNIVAC 1108. It doesn't work. Make it work. And in pouring into it, I discovered it wasn't exactly algol at all. It was a Case Western Reserve algol that had been doctored to make a language called Simula 1. And it had documentation that looked exactly as though it were Norwegian transliterated literally word for word into English, which in fact it was. So we couldn't understand it, but the debugging technique back then in these big engineering buildings was you could take a listing. Remember those fanfold listings? Nice piece of computer graphics, because you could take these things and unwind them down the entire hall of the building, and you could put graduate students on different parts of this listing. So about 3 of us crawled over this listing on our hands and knees, saying, this looks like it might be the storage allocator, and here's where they do this. And finally we realized from the storage allocator that it was actually allocating storage the way Sketchpad did. And we suddenly realized that this funny name, they had funny names as was mentioned this morning. So they had the word process, which didn't quite mean what it meant to us, which we would use the word instance for today. And they used the word activity for what we would use the word class. Now, I happen to like the word activity, but we had no idea what this meant until we saw the analogy. And then I had one of these epiphanies, because I had been thinking about molecular biology until recently, and Simula was kind of, question is it a better old thing or almost a really new thing? And this is the dichotomy you always get when you run into something new. And all of a sudden I had this idea that, wow, what if you threw away algol and stayed with what the powerful idea here was, that Simula was actually making things that were like little software computers, and it would make as many of them as you wanted. And that's what Ivan Sutherland was doing with computer graphics. And a computer, obviously, by the Turing argument, could do anything, and so you could get rid of data structures, which I hated because they were so fragile. And all of a sudden I realized if you could just find a way of making everything out of little computers, you would have a much simpler abstraction than the paraphernalia that was in use on computing at the time. Turned out to be difficult to do pragmatically. It's not easy to make the number 3 a little computer and have it run fast and have it be small in those days. But that was the insight. So that was one of those holy cows. And another thing that was around at that very same time was Doug Engelbart's online system, also funded by ARPA. And this thing was incredible. So the mouse was invented by Doug and Bill English in 1964. So the mouse is a couple of years old when I first saw it. One of the things that they used with this hypertext system was they used it for dealing with their structured programming. So they had done their own compiler, and they made it so that you could actually get abstractions of different levels of detail in their code, which I thought was pretty interesting. And they used this thing for conferencing. So here's what NLS looked like. Should be some sound here, but in a minute. So this picture could have been taken yesterday, but it was actually taken in 1967. There's Engelbart with his mouse, and he has a 5-finger keyboard on the other hand.
So I can say, I'd like to go to produce, but I'd like to go to produce, they get big. I'd like to say one branch only, and let me look just that low, and I see it.
Okay, I'll say a word or two here. So this is actually in many ways a better user interface theory than we use today. 3-button mouse, 5-finger keyboard. And Engelbart's idea was that you shouldn't be moving your hands back and forth a lot. So he wanted to be able to do all the navigation you're ever going to do from having your hands outspread. And he also wanted to be able to do simple typing. So correcting, so you could type every character out here, and you could do all of the manipulation and command giving in the system. And the command giving was subroutine style. So a typical command was move character. That was the name of the subroutine, and then you'd pick the character you're going to move, you'd pick the destination, those are the 2 parameters, and then you'd hit command accept, which is this button all the way over to the right on the mouse. So it's interesting how the underlying programming affected the user interface style, and we'll see that happen over and over again.
I can say, I'd like to see one line only.
So it has filtered
views. Another
views.
thing I can do. There's a root I said I have here. So here, I'm afraid I'll need a different picture of the view. So here's what I do with a picture drawing capability here. It's a slight map if I start from work. And here's the route I seem to have to go to pick up all the materials. And that's my plan for getting home tonight. But if I want to, I can say, the library, what am I supposed to pick up there? I can just point to that. And oh, I see, overdue books and all. Well, there was a statement there with that name on it. Go back. What am I supposed to pick up at the drugstore? I see, very interesting. All right. Market can do things if I want to just say, I'd like to interchange produce and canned materials. Bingo. And numbered rightly if I care to look. Interchanging them very quickly. Cans are going to get interchanged with produce. They do it and all gets renumbered.
So I'm hoping everybody here noticed that the response time on this system is just a little faster than you're used to. This is on a 192K time-shared computer with 20 users, a half MIP machine. But they got sub-second response on everything. Why? Two reasons. One is they wanted to. The other reason is that they could really program. This is how you can tell. You can't tell whether you have a research center in a company just because there's something called research. You can tell when the company gets in trouble and the chief executives do not raid that thing called research, then you know you have a research center. Otherwise, it's just a toy. The same thing with user interface. It's not a user interface just to make a control panel. You have a user interface where the people doing the user interface really care that there's a person at the other end of this thing and really cares about what the person needs. So one of the distressing things about this system, this movie I'm showing you was part of a demonstration, a live demonstration to about 3,000 people in San Francisco in 1968. So this movie is about 33 years old now. And if Tim Berners-Lee and the other people who did the World Wide Web had had the slightest curiosity, as they should have, I'm sure, did in physics, to find out what people before them had done, they would certainly have found out what Engelbart did, and the World Wide Web would be much better today. But instead, it was done really terribly, done as a consume-only medium. 25 years of progress in being able to author on a personal computing, and all of a sudden the web comes along and we're consumers. Again, think about that. All this, the hyperlinking and hypertext stuff and conferencing and all of this stuff have been done in a full-fledged, well-funded project back in the late 60s, and it got completely missed by the current wave of very active but very ignorant people doing computing today. Now, the other thing that happened in 1964 was the tablet was invented at Rand. So this was a honey of a technology, but unfortunately, even in 1967 or 68, it cost about $18,000, which is like $100,000 today, to get one tablet. So many wonderful things were done on this, but usually each research center only had one of these. And it was one of the reasons why the mouse made it and the tablet didn't. It was just too difficult to make tablets for a long, long time. Now, another thing that happened at Rand, even a little earlier, was there was this old machine called the Joniac, which is one of the original Princeton machines done in the early 50s, and they were about to take it out of commission in the late 50s, and Cliff Shaw said, "No, give it to me." He's the Shaw of Newell, Shaw, and Simon. "Give it to me, and I'll do something with it." So what he did was a truly wonderful interactive, the first really great interactive programming language for end users, which is called JOS. So JOS looked like this. Here's Cliff Shaw. Actually says more words on this video than I ever heard him say in his entire life.
We call the system JOS, standing for Joniac Open Shop System. It is an online, time-shared use of the computer. Joniac is a venerable machine, but small and slow by today's standards. Coupled to it is a special-purpose buffer for messages to and from remote consoles. Each console consists of an electric typewriter and a few buttons and lights. At present, 8 such stations in various locations in the Rand building are connected by telephone lines to the buffer. An executive routine in JOHNNY-AC serves up to 8 users at a time by interpreting and carrying out commands given in a simple language.
I think I'll pause. You can't really see that. What was beautiful? So what was beautiful about this system was about everything. So at the end of the paper that Cliff Shaw wrote about JOS, published in 1964, he said the important thing about user interface design is the little things, the hundreds and hundreds of little things. So for instance, in this system, instead of using teletypes, they refitted a bunch of IBM executive typewriters, so you could have really good-looking typefaces. They printed on drilled paper that would fit into notebooks done by these end users. When you typed on the machine, it typed in green, and when it typed back at you, it typed in black. And every little detail was handled beautifully on the system. So there's one of the few systems in the world when in the morning you realize, oh, in the afternoon I'm going to get a chance to use JOS. You get this little tingle of anticipation. You knew, how many times have you felt that about a computer system? You just knew this was going to be a beautiful experience because everything was thought through. And he didn't try to do anything that he couldn't do in this perfect way. So this set a standard for many, many years in every respect, including documentation. There's JOS. Then another thing that had appeared on the scene in the early 60s was my vote for the first personal computer, which is called the Link. This is done by Wes Clark here. And one of the design criteria for this machine was that you had to be able to see over it when you were using it. So his idea was you didn't want a machine that towered over you when you were using it. You would be towering over it. And it had most of the paraphernalia on it that we associate with personal computers today. So it's my vote for the first personal computer. And also in 1965, we had the first statement of Moore's Law. Then a few years later, the second statement of it. And what happened is kind of in the middle here, between doubling every year and doubling every 2 years. It's been doubling about every 18 months. So this gave us a 30-year roadmap to be able to understand what kind of computing systems that we could do. Then the other thing was that ARPA had decided to finally do the ARPA network. And so suddenly we were thinking about how could we run a system that might have potentially millions of machines on it. So all of those were context for the ways of thinking about complexity. And that led to this machine that Ed Cheadle and I did, what was called a flex machine. And so I decided to imitate how Simula got implemented, where they had some deep insights about objects, and they took ALGOL as a kind of a structure, and they made the Simula 1 system that I was familiar with. And I wanted something like JOS. And that very same year, and I'm sure Klaus remembers it better than I do because he had to write the paper, but the same year that the Simula paper was published in the ACM, which was September 66, in January and February, Klaus Wirth and Weber had published a fantastic, in-depth treatment of a language that they designed and implemented called Euler. And Euler was an extreme generalization of ALGOL. So it was taking ALGOL towards Lisp in a sense. Basically, it was based on some earlier ideas by Van Wijngaarden and an earlier paper that Klaus had written, which was called The Generalization of ALGOL, published in the year 65 or something. So this was beautiful stuff because basically it got down to the essence. And if you looked at Euler, you would see something that had the clean simplicity of JOS, except it was powerful. It was really powerful. And I thought, boy, if we could make Euler object-oriented the way Simula had made ALGOL object-oriented, we would have something that was both very powerful and also very small. because Euler had this very nice way of compiling. And it happened that the third computer I'd ever learned was the Burroughs B5000. And the way they had decided to implement Euler was to make a microcode for an architecture that was somewhat like the B5000. So this is very pretty. So this is really the origin of the bytecode interpreter stuff that is so prevalent today. It used to be called pseudocode in the old days. So I thought this was just the greatest thing. So Ed Cheadle and I actually built the hardware and the software of this machine. Here's a picture of it on its own display. And since Windows were already around, we put them in. They weren't overlapping because the displays back then they were calligraphic displays. It was very, very difficult to make an overlapping window, and I never thought of the idea at that point. But using objects at the lowest level in the system and combining the language with this idea of coroutines, so I realized that if you had coroutines and persistence, you didn't need files, because you basically just paused every structure that you wanted to stay around and just let it stay active as a way of getting away from data structures. So there are a lot of interesting ideas in this thing. And on each iteration of these languages we did, we implemented the hospital simulation from the Simula 1 paper, because that was where we finally understood Simula 1, was following those patients around the hospital. We'll see it not too long from now. So I'm going to skip over some of these insights we had about objects, and maybe if there's time at the end, I'll talk about them. I'll just say one word, that the more you can think biology when you're trying to understand objects, the better off you are. The more you think C or indeed any programming language with objects grafted on, the further away you are from these things, because you're basically trying to understand systems that are robust and even somewhat redundant. Now, the summer of '68, we had a version of this flex machine going, and I gave a report on it at the ARPA graduate students conferences that summer. And that summer, I saw this first flat panel display. So all of a sudden, flat panel display. Wonder how long it would be before you could put the flex machine on the back of this display. Then the other thing I'd seen right before going to this graduate conference was what the RAND people had done with their tablet. This is a system called Grail. So in '66, so they built the tablet in '64. In '66, they implemented this really tremendous character recognition algorithm, better than graffiti, and of course, infinitely earlier than graffiti. And then they decided to do a graphical programming version of JOS for their analysts at RAND. And here's what it looked like.
First, we erase a flow arrow, then move the connector out of the way so that we may draw a box in its place.
So it recognizes he wants a box and just makes one. Now it's recognizing his handwriting.
The printing in the box is being used as commentary only in this case.
Might notice how efficient
The box is slightly too large, so we may change its size.
That's where modern-day window control came from, literally.
Then draw a flow from the connector to the box.
Notice the
Attach a
gestures are
decision element to
idiosyncratic.
the box and draw a flow from it to scan. We then erase the flow arrows attached to the process post new area and move the box to a new position. This allows us to draw a new box.
This is an incredible system. And there's a wonderful 15-minute movie that I'm in the process of digitizing and giving to the Computer Museum. But look at this system, all of a sudden you realize, my God, these guys got an enormous amount of what user interface design has to be like. And again, it was because they were trying to make this system as nice for an end user as JOS was, but now on the displays. They just thought of every little thing, and this is smooth, and it just really did work as fast as you saw there. And any one of us would like to have this system today. But in fact, most of the systems that are pen-based today are quite a bit inferior to what these guys did. Then in the fall, I saw Seymour Pappert's work with Logo, and Logo was an adaptation of JOS to Lisp for kids. So a typical Logo program to draw a circle used differential geometry, go a little, turn a little over and over again. If you tell that to a turtle, which is actually a vector, you're adding little incremental vectors to it and turning it a little, you're going to get a perfect circle, because a circle is that thing that has constant curvature. So when I saw this, I was seeing somebody using computers to make Montessori-like toys for children, and it captured my imagination more strongly than anything else has. And on the plane coming home from that visit, I started thinking about what would a computer for children actually be like. And I decided it had to be something they could carry around. So we made this cardboard model out of and filled it up with lead pellets until people didn't want to carry it around anymore. And so the weight, the maximum weight, was 1 kilogram. So anybody here have a 1 kilogram computer yet? So analogy to musical instruments, the idea of children learning math and science by doing their own simulation games, using real science, all of those things were part of this. And then this realization that we might all be dead before the real revolution happens, because back in the manuscript days, when the printing press appeared, it was 50 years to go from a big Gutenberg Bible to the eldest book that you could put in your pocket. But the real revolutions from the printing press didn't happen until more than 100 years later. And so we had this image that here's the mainframe, which is kind of the old manuscript thing. Here's a desktop computer, and here's a computer you can carry around like the eldest book. There was this image that, gee, the real computer revolution might not happen until the middle of this century, and we'd all be gone by then. So there's a real urgency to try and do something about it. And we got that chance at Xerox PARC. So one of the best things that ever happened right around in that period was here's the cardboard model of the Dynabook, and here's the real HP 35 calculator. And I had two interesting things happen with the HP 35 calculator. One is that I just happened to have it when I had a talk with my insurance agent. And without thinking of it, I pulled out the HP 35 and put it on the table between us. And all of a sudden, he was talking to me very differently about insurance, because I could just sit there and calculate anything that he said. And I realized that all of a sudden, the balance of power had shifted. Then the second great thing that happened is about 3 weeks after I got this early HP 35, it was stolen. And I realized, at last, somebody has made a computer that's stealable. We're making progress. So let's see. Now, a few things had changed in the way I was looking at languages. Remember I said that Euler had gone quite a ways towards Lisp, and I didn't really understand Lisp at that time, and a few years later I had occasion to go in and try and understand the Lisp interpreter written in itself, and I finally did understand it, and then I had this huge thunderbolt that what you really needed was late binding and everything. Not just because you need it for end users, but because it was one of those things where I suddenly realized, hey, we don't know anything. Every time we do something, it's a huge learning curve. And when we do it in an early bound form, when we get to this place where we suddenly learn the thing that we needed to know at the beginning of the project, the early boundedness of what we've done discourages us from going back and redoing things. It's just too much work. So you say, oh, I'll do this in the next system. But I realized that the early boundedness of Lisp, coupled with the right kind of programming tools, and you could actually take an inspiration 3/4 of the way through a project and reformulate your code much, much more easily. And that was quite possible to do because we were building our own computers. So we built the Flex machine. It had a microcode processor in there, so we were actually the firmware was actually giving us something like a custom piece of hardware, and we were planning on doing that at Xerox PARC. And so the idea was, let's do a kiddie computer that we can actually build in the early 70s. So the first one was built around a Sony Trinitron, 9-inch Trinitron. And then the realistic design I did here looked like this in 1971. That had the Trinitron in there. It had some room for either this mythical 3M tape drive, which finally did materialize, and so forth. But the idea was to make a computer that we could actually put into schools. And we had to understand about displays. So here's this wonderful old machine we used to call the old character generator, and it was just the highest bandwidth video that money could make. We built it ourselves, and the first thing we did was to try and do really high quality fonts. And the second thing we realized is that we could, by turning it upside down in a way, we could make one of the first bitmap memories ever done and do painting. So here's what it looked like to design a character back then. This beating is because this was done on a 16 millimeter Bolex movie camera back then. So you just designed the thing in, and it showed you the thing in different sizes, and then rendered the thing. So we did many experiments with that, understood a lot about, for example, one of the things that we found was that the worst display pitch you could have for a human being was 50 to the inch at normal viewing distance. That was the one where you could see the square edge on a dot on a pixel. Of course, you don't want to see pixels when you look at a display. You want to see pictures. And so 50, and it happened that 50 to the inch was the exact pitch that IBM had chosen for all of its displays. So they were the worst looking displays that money could buy. But there was a nonlinearity, so we discovered that if you made the pitch 100 to the inch, you'd be having 4 times as many pixels, which is expensive, but the inability to see the square corner went down by got better by a factor of 10. So 4 times as many pixels gave you a factor of 10 better response. And so we realized that just by choosing these very, very carefully would get some very important. Let's see what this is. So here's using it as, you also see the character recognizer that we built in here. So L for drawing lines. D for sketching. So here's the first painting system. So this was done the summer of '72. Choose brushes and choose different paints. Okay, and then we built a bunch of these machines called the Altos. And here's what they look like. And this is the Alto doing real-time musical synthesis. So this is where we did stuff with really young kids, kids of age 3 and 4. This is a button box that has iconic control on it. The altos were kind of a joint. The hard work was done by Chuck Thacker, who was kind of the hardware genius at Park, and one of the 2 or 3 people that Park could not have functioned if he wasn't there. And the design for the thing was sort of the clash of 3 friends who also had strong wills, myself, Butler Lamson, and Chuck Thacker. We all kind of got what we wanted. The main thing about the altos was that they're cheap and pretty fast compared to time sharing, and they had 500,000 pixels on the screen. So this allowed us to do many, many interesting things without having to optimize for several years. I believe that one of the principles for getting ahead in this business is avoid optimizing while you're trying to design, because your optimizing hat, once you put it on, you're a different person. You're just not the same. You're in the pink plane when you're optimizing, because you're trying to deal with known facts and make those known facts happen. And so Park was able to make a lot of progress just by having a bunch of these machines around and having them be fast enough for a few years so that new ideas could be done very, very easily. So I'll show you a couple of examples. Like here's this is the first test of overlapping windows. The inspiration I had in the shower the year before. And this is before we put window boundaries on. So this is like the Alto is about a week old when we did this. So these are 2 pieces of text. And I'm going to pick up one by its corner the way Grail did, showing the clipping there. And then I'm going to move this over the other piece of text here. It's not too convincing at this point. So now I'm going to bring the other guy up on top, just to prove, and then bring the other guy up on top. So the original plan was to have the windows show full graphics and be dragged. And we had to abandon that because we couldn't quite pull off the animation in real time on this machine. So here's some of the earlier tests for windows with boundaries. You can see the user interface on these, that the Grail style, make it bigger and smaller by the lower corner there, move it around by that corner, get another one by that corner, gives you another little window. And here's a first class of kids. So this is a 12-year-old taught by a 13-year-old. So she had taken the class the year before. There she is, Dynamic Maryland. This is what she had done when she was a 12-year-old. So this is the first graphics system done by a child. So in other words, she did this application. So it has different shaped brushes up here. It has different forms. So she grabbed the square guy, and now she's drawing a picture with it. So a lot of our interest was in end users being able to make their own tools. Here she got the hexagon brush, is drawing tree trunks with the hexagon. Now she's getting a little dot, drawing the trunks. So this is basically a paint program done by a 12-year-old. And then in her class,
you can write box on the screen too. You can type box to do it, right? Just write it off.
So here's something that's like a drawing, an illustration system done by another 12-year-old girl. So she's got little selection handles, and see she has a little menu down here of different commands. So she just changed the color. Now she's going to change the size of the thing, make it smaller. You can see a color bar menu up on the top. Now she's moving the thing. So again, this thing was completely designed by a 12-year-old and built as an application. But it also shows you the user interface approach here, which we used to call doing with images makes symbols. You basically stay in the domain that the users want to operate in, and they learn the symbolic stuff as a way of getting more power over it. Now here's a more sophisticated thing done by a 15-year-old. So this is a circuit. This kid was interested in ham radio. So this is a circuit drawing program that he did. So he has a menu of circuit symbols down here, but you'll notice in a second he also uses a pop-up menu. Here you can see his hand doing things. You can see that you can get this pop-up from the middle button on the mouse, so he gets a closed dot there from it. We're pretty excited to have a 15-year-old do this. He just grabbed a resistor over here and made an instance of it. So it's bridging this gap. So this is trying to do as many things as you could along the lines of Sketchpad, but allowing the end users to do their own tools. Okay, now the Alto was microcoded, so you could actually, and it had multiple display buffers, had actually display list architecture that allowed you to do real double buffered animation. So you got the following animation response on it. So I could do about 120 square inches of graphics in 2.5D at about 12 frames a second, which is what you're looking at here. So how do you make these animations? So this was done by a very talented guy by the name of Ron Becker. There's a menu up at the top you can't quite see here, but he's drawing a ball and putting a little specular reflection on it. Coming over here, and he's clicking on the pop-up translucent menu there to get this show me a path icon. Now he says, okay, now run it. So now it's taking this ball through the path. Now he wants to get the step icon here, to single step this guy. Now he's going to zap this guy and replace it with an empty frame. And now he's going to get another translucent frame and lay it over this one. Start the animation. You see that frame is missing, but as he starts painting over here, that painting will be laid in, and he's using this guy underneath as a guide for where the center of the thing is. So you see as he paints, the painting as his painting is being put into the animation. The trick of animation is to put enough similarities in the different frames so that your eye will seem to make one frame distort into another. It's sort of cognitive morphing. And you notice that even though it's only one frame here, you seem to see the ball deforming. It's called squash and stretch. Another 12-year-old girl.
It's a horse galloping. I can write a program that has the horse galloping across the screen. Here's the horse again. And now I have a jockey.
So here's a feature she added, which is to combine two animated things into one.
The jockey on the horse.
Drops them in.
To make a racehorse.
Now they're one logical entity.
now I can have the jockey and the horse run across the screen by making another program.
Okay, and one more media thing here. So again, because we had microcode, we could do real-time music, and we invented a form of FM that could be played in real time. We had 8 voices of this real time. And right now we're going to make a kind of a cello. Again, you get to see the user interface here. We leave the old guys up because we want to see where we're coming from. That gives a gradual, kind of gradually getting louder, bowing thing. And now we want more harmonics. This is kind of this one he's drawing here is a measure of harmonic. So we want more harmonics in the beginning and then less harmonics, so you get the bow biting. Now we want to try various modulation families. This is pitch. Swoop up to the pitch so the string comes up to speed gradually. Put a little vibrato in this repeating section between the 2 lines. Now let's go look for some ratios that sound string-like. Here's one that's kind of clarinet-like. So we don't want that one. But this 1 to 3 one is a kind of a nice string sound. And if you just plug this, now we play the fugue from the Pascalian Fugue in C minor with a different timbre in each voice. Wonders of personal computing. So here are a couple of these altos in the schools, and from our standpoint, we'd actually gone to quite a bit of trouble just to get a couple of computers in a classroom in Palo Alto. Right? Basically, you have to invent both all the hardware and all the software and build all the stuff, and you eventually get a couple of computers in the classroom to start actually working with the children. So, a couple of things here. These kind of slides are the most boring slides because they just have text on them. But the notion of objects here is very simple, and it actually required microcode to make work. So the idea is there's nothing that isn't an object. Everything. There's no thing in the operating system part of it that isn't an object. The number 3 is an object. The Boolean value true is an object. And objects can send and receive messages, and objects can remember. That makes each object kind of like a computer that can communicate. And then we actually call these guys classes. Should change this to class here. This below-the-line stuff is stuff that we fooled around every version of Smalltalk and subsequent systems we've done. Ones up above we've never changed. These seem to be 3 good things about objects. And the classness and what a class should be and exactly what it is. Classes are objects in Smalltalk, and the meta system and everything else we've changed numerous times over the years. And I think everybody who's fooled around with this stuff finds that it's difficult to come up with exactly the abstractions that you really want. But this language stuff actually influences the user interface. As you noticed, the in an object-oriented system, you say the object first. It's actually the subject. We should have called them subjects. It's actually the subject of the sentence. Then you say what you're supposed to do. And in the GUI, you select the thing that you're going to talk to first, unlike the way Engelbart did it, and you send the message with a mouse click. And the object is the thing that contains its menus. So you get an idiosyncratic menu, etc., etc. And GUIs are successful in an object-oriented systems if you use polymorphism as much as you possibly can. And I don't have time for this, but basically this is first starting off with the Piaget stages and then realizing that Brunner's multiple mentality model. So the book here is called Towards the Theory of Instruction by Jerome Brunner, still in print, and it's a really great book. Best book I know of about education. It has nothing to do with computers in it. But he shows a bunch of the experiments that show that unlike Piaget's stages where you start off doing and then you move to an image stage and you go to a symbolic, Brunner showed that all of these mentalities are actually active, and what's really happening is a change of dominance between the mentalities. So if you do your user interface design right, you can use all three of these very strong ways that humans have to think about things. And this is just to remind everybody that icons were around a lot longer before Park. Sketchpad had them, and this was a wonderful system called the Lincoln Wand that had a 3D tablet stylus. So this thing sensed where your hand was in the air, and it had a whole iconic menu interface over here that you would just point at. And so that these ideas were around for quite a long time. And the Park GUI had these characteristics. We called it modeless, not because there weren't modes, but because you didn't have to do something to get out of the mode. For example, this guy is on top of this guy. So I can select text in here. And if I want to do something for this guy, I just go directly at this guy. I don't have to do anything to get out of here. I just go for the first command that I want to do here, and the system does it. What you see is what you get as much as possible. Here's one that hasn't been done very well today. If you can see it, you can change it. So this is the idea that always have authoring be symmetric. Every view should be overlapping. So don't worry about whether they're windows or not. The whole deal is layout and compositing. Iconic reference for things. This is a reference to the place I just was. And multiple projects was a key part of the interface at Xerox PARC. Not done, unfortunately, on the Mac or on Windows. The reason I have them here is I'm using a system that is not using any of the Mac code. So this is actually an iconic reference to this project I was in. And if I press on it, well, maybe nothing will happen. Oh, because I can't see it. Okay. Now I'll press on it. So I got taken back to where I was. Down here I have a thing that says go back to the previous one. Takes me back there. So forth. So here are a couple of, this is the first desktop publishing system. And here's a technique that we use everywhere, which is to have the iconic menus come up around the object that you're using. So if you're in the text, you get a different menu than you were here. The idea that everything is basically layout. It's all part of that user interface. The idea of retrieving from templates that look like the thing you're trying to retrieve. Parallel time, this is about 1974, 75. Parallel time, a guy by the name of Zloof at IBM was doing the same kind of thing. Simulation was the name of the game here. Here's this was a fun one. This was the part of the hospital that was actually done by children. Recapitulating this hospital simulation from Simula 1. And here's a more complicated version of this thing that we had done. So I think just about, let me skip through a few more things here. I want to give you a little hint of the parallel work that was going on at MIT at the same time. Nicholas Negroponte was on our advisory board for our project at Xerox PARC, and I was on his advisory board for his project. And he had a big color buffer back in the early 70s. And using this color buffer, they did a system called Spatial Data Management System, and I'll try and show you a few of the highlights in my last 4 minutes here. So here's the map. Over here are the controls. He's got touch pads on the things. This is about 1977 or so. He's got a huge full wall screen here that shows him where he's navigating around on the map. So you get a sense of this. So this is a zooming interface. First really good one ever done. So the idea is everything that you're interested in is in this thing they call data land. And as you navigate over something, you can zoom in on anything and it will just retrieve things of higher resolution as you go, so that the zoomed out things are their own icons. So now he's zooming back out. It goes to a lower resolution version of this thing. Here's a map of MIT. You can see where he's navigating here. Now he's going to go up to his ARPA correspondence on his desktop here. Here's a letter from, I think, Steve Lukasik or whoever was there at that time. So again, you zoom in on it. Crispin's up. This is also the first anti-alias text. And again, because Nicholas really cared, they anti-aliased everything. So in many ways, this is the most beautiful single interface design that was done in the 70s. You can see it's perfectly modern. It would be great to have it right now. So they dove into their report for ARPA, which in this new ARPA of the late 70s was the size of a book. And he has his controls for the book here, so he can point at topics for the book and it will flip the pages. Here's what it looks like on the main screen. Let me zip forward a few. So touchpad is what you use for flipping pages. Speech recognition.
Take me to the museum.
So it goes to the museum. Telephone interface. Brings up the interface here. So they had 8 bits per pixel. Let me zoom up to a... So they used it for doing anti-aliasing and for doing modern graphics. So this is the first thing where they actually had graphics designers looking at the interfaces. So they're nice and clean and simple, very understandable. Calculator. Zooming in on a map. Here's a television set. Just hooks you up automatically to TV.
LAPD.
Get Columbo.
Yes.
Maybe that's a good place to stop. Thank you. Thanks. I do.
Thank you very much, Alan. Now we have another coffee break and we reconvene at 4:10 for the talk of Rudolf Bayer.